Assalamualaikum and very good evening to all of you. Welcome back to the class BAA2213 Reinforced Concrete Design 1. In our class today, we will discuss and focus on the exercise number 8 and exercise number 9, which is the shear reinforcement for beam. Okay, can you see my screen now? Okay, for the shear reinforcement, okay, I believe you already watched this my previous video, okay, and already go through this slide. The important thing to know is this one, okay, this slide, okay, slide number, okay, this one, slide number 17, okay, before the example, okay, it's slide number 17. This is the criteria for design of shear reinforcement inside the beam. Okay, first of all, we must check the VED. VED is the design shear reinforcement. As in beam, we have MED. MED is the design bending moment we obtain from the structural analysis. Okay, so this is the, okay, we obtain the VED from the structural analysis. And then the VED is the capacity. Okay, the capacity of concrete itself to resist shear force. So if the action shear stress, okay, is greater than the capacity, so we need the shear reinforcement. However, if the capacity of the concrete is larger than the shear stress, okay, we obtain from the analysis, so we don't need the shear reinforcement. But for the beam case, we have to provide the minimum reinforcement for the beam, where we can obtain by using this equation. Okay, the ASW is the area of steel for shear reinforcement. Okay, then the shear reinforcement, I believe you know. Okay, this one. Okay, this is the shear reinforcement. Okay, it will. Okay, we will provide the loop. Okay, so like this one. Okay, so like this, we have a very long, okay, let's say long steel bar. So we will bend here, maybe here, and another here. So we will convert as a loop. Okay, and this is our main reinforcement. Okay. So and if our VED is greater than the capacity of concrete to resist for shear force, we need the shear reinforcement, and then we must check the concrete strut capacity. Okay, we must know the value of theta here. So if the capacity for theta equal to 22 degree is greater than the VED, so we design the minimum links and we use theta as 22 degree, and then we can use these equations to determine the steel reinforcement of shear. Okay, but if the, okay, we check, and then first we check the this one, VRD maximum, okay, the concrete strut capacity. First we check for theta 22 degree. What is the value? Okay, and then let's say here, this is the value 22 degree. And then for the, we check for the 45 degree. Okay, if the VED is lesser than the 22 degree, automatically we choose this one. Okay, this is option number 1. Option number 1, we design minimum links and we just use theta equal to 22 degree. However, if our VED is greater than VRD max for theta 22 degree, we have to check for the theta 45 degree. Here, this is the answer. If our VED, okay, is between 22 and 45 degree, so we have to use option number 2 in designing the shear reinforcement. where we have to determine the new value of theta, and then we can use the new value of theta in order to determine the ASW over S. However, if the VED is greater than the theta is greater than the concrete strut capacity for theta 45 degree, so we have to increase the size of beam or use higher concrete class because the capacity is insufficient. Okay, this is the all three options. Okay, four options, actually four options, including this one. Okay, but this one is very rare to find inside the beam. However, we will find this situation inside the slab. Okay, any question? Okay, if no questions, then we can try our exercise number, first exercise for today, which is exercise number 8, okay, in total for this semester. Okay, okay, the exercise is based on exercise example 1.5 in the module. However, I like to change some parameters. Okay, I give you time to write down the parameters. Here, I change the the length is equal to 6 meter now. Span of the beam. This is simply supported beam. You must know how to analyze the simply supported beam in order to get the bending moment. Okay, MED is very simple. Use the equations WL square over 8. This is the equations. You must remember. And then, okay, W is this one. Okay, the ultimate load. And then L is the length. And then 8 is coefficient, fixed. EED is equal to WL over 2. These two equations is very simple. You must remember. Okay, and then the ultimate load here is I change to 120 kilonewton per meter. Okay, and then the AS for compression. Okay, sorry. The B times D here I change to 2 to 5 times 500. So our B is 2 to 5 mm. Our D is equal to 500 mm. Okay. So you must know, I believe you know how to determine the value of D. And also if it involves the D prime, I believe you must know how to determine the D prime. Okay. From example number 1 to example number 7, the value of D prime and D is given. Also in this example also is given. But in the real situations or real evaluations, you have to determine the value of D prime and D. Okay, and then the design load is, okay, the span is 6 meter now. The design load is 120 Newton per meter. And then sorry, still for compressions, now I use 2H16. Okay, what is the value of AS prime now? Anybody? What is the value of AS prime now?
402.
Sorry?
402.
402. Okay, thank you. 402 mm square. And then the tension steel, I use H6H20. Okay, find the value. Please help me. Okay, so this is our arrangement of steel bar. Okay, let's say here, I do it here. This is, okay, for today, we only focus on the rectangular shape of beam. Okay, on this Friday, this coming Friday, I will focus on the flange beam. Okay, so this is, okay, our main reinforcement. Okay, 2H16, and this is we use at the bottom here 1, 2, 3, 4. Okay. Okay, 6. Okay, means this 2H20 plus 4H20. Okay, total is 6. And then this is 2H16. Okay, and then the concrete grade I use is 30. Okay, Newton per millimeter square. Okay, which is the concrete class C30/37. Okay, and then the design of steel is similar. Okay, have you finished writing this design parameter? Okay, I believe everyone has finished. So we can start with the, okay, our answer sheet. Okay, exercise number 8. Okay, the solution is, okay, just follow, okay, the similar step. You can refer to this tutorial later. Okay, example 1.7. But now we do it together. Okay, and you can stop me. Okay, the solution here is, first step is we determine the design shear force. Okay, VED is equal to WL over 2 equal to W. Okay, W is 120. Our L is 6. Divide by 2. Okay, what is the answer now? Okay, good. Thank you. 360 kilonewton. Okay, and then number 2 is we check the concrete strut capacity. Okay, shown here. We must check here. Okay, we must check here first, but of course we may jump. Since this is the case of beam, it's very rare, okay, to have no shear reinforcement for beam. So we can jump to this one. Okay, if you want to check, you can check by using, okay, this equation. Okay. Okay, so this one we check the step number 2 is we check the concrete strut capacity. Okay, how to check? We use this equation. Simply use these equations. Okay, first we check for this one. We use for these equations. This one. Okay, I hope you can see. Okay, we can use these equations. For the first, we check for theta equal to 22 degree. Okay, so what is the equations? Okay, just write down the equations. VRD max is equal to 0.36 dw dot d, okay, 1 minus fck divided by 250, okay, times fck divided by cotangent theta plus tangent theta. Okay, you can use your calculator. Okay, cotangent theta is equal to cos theta divided by sin theta. Okay, this is the equation you must remember. This is very useful. So the theta here is equal to, we check for theta equal to 22 degree. So the tangent theta is equal to what? 0.4, and cotangent theta is equal to 2.5. Okay, and then so the VRD max is equal to 0.36 times the BW is equal to, what is our BW? BW is 225, okay? 225 times our D is given as 500. Then following this equation, 1 minus 30 divided by 250 times FCK is 30. And then cotangent theta is 2.5 plus tangent theta is 0.4. Okay, may I know the answer? Okay, class, anybody? Anybody have the answer for this one?
369 kilonewton.
369 kilonewton. Okay, thank you. So 369 is already greater than our VED. Okay, according to this rules. So option number 1, because our VED now is 360 and lesser than the VRD max. So okay, this one is greater than VED. So we can design. Okay, we can design minimum link, and you use theta equal to 22 degree automatically. Okay, so now we can go to step number 3, which is design shear reinforcement. Okay, so just simply use these equations, okay, to get the ASW over S. ASW over S is equal to VED divided by 0.78 times FYK times cotangent theta. Sorry, I missed the D here. Okay. So equal to VED is 360 times 10 to the power of 3 and divide by 0.78 times D 500, FYK also 500, cotangent theta is 2.5. So what is the ASW over S now? Anybody? Naim ada ke sini? Anybody have answer for this one? Please help me.
0.74.
Okay, 0.74. Thank you. Okay, so this, okay, 0.74. So now we have to, okay, we try using H6, and then we got ASW is equal to, okay, we have to refer the, refer this table. Okay, you must have this table. You can just download, okay, this table. I believe you have this table. Okay, sorry. Okay, H6. So the value of ASW is area of steel for shear. ASW is equal to 50. This one, 56.5. Okay, 56.5. We select the 2. We select the value of 2. Okay, please be careful for this one. Okay, we select the 2. So the SW is 56.5. So write down here 56.5 mm square. Okay, we select 2 because, okay, maybe this one can help. Okay, because we have this one. Okay, we have the loop. Okay, number of loop if we have 1 and 2. Okay, so that's why the ASW we must refer to 2. Okay, if our design is like this one. Okay, let me do it here. Okay, if our design is like this one, in some cases you might find this design of beam. Okay, here maybe you have 1, 2, 3, 4. Then 1, 2, 3, also 4. Okay, maybe 6 here at the bottom. So your steel reinforcement might be here, might be like this one. 1 and another 1, 2. Okay, as a loop, sorry. Okay, this one. 1 here. Okay, the steel go as a loop. Okay, so this one is ASW and this one also ASW. So we have 1 and 2. So that's why we refer to 2 number here. Okay, the total of 2 is 56.5. And however, if we have another okay, still here. Okay, maybe the shear force is too high. The shear force is too high, so we have to use 4. Okay, 1, 2, 3, and 4 vertical steel for shear reinforcement. So our ASW we must refer to the 4. Okay, the value of 4. So the new is equal to what? May I know? If you use H6.
113.
Okay, yes, 113 is our new ASW. Okay, you must be careful about this one. Okay, thank you. So we must proceed here. ASW, so we can check the spacing. Okay, the spacing here is spacing S is equal to, so we just use this equation, SW over S. Okay, so S is to the top, the spacing. ASW over this one, 0.74. 0.74 is equal to 55, 50, 56. Okay, 56.5 divided by 0.74. So what is our spacing now?
76.
76. Okay, mm. So we use S equal to 75 mm. Okay, because the increment, okay, in order to ease the job of our labor, okay, our construction workers, so the spacing is also in increment of 25, 75, 100, 125, 150, and then 175 until the maximum. Okay, but the increment is by 25 mm. So the construction will be easier. Okay, the construction workers will install it easier. Okay, compared to you use the spacing is equal to 76.383. This is impractical on site. Okay, so we check the S maximum. Okay, according to the code is equal to 0.75D. Okay, you can check in the Eurocode letter. 0.75D, maybe here. Okay, this one. Okay, this clause. Okay, clause equation 9.8. Okay, clause 9.2.2, page 156. Okay, because once you are working later, you must know which part, which page to refer in the code, either BS code or the Eurocode. So this is the maximum is 0.75D, but must be lesser than 600 mm. So 600 mm is the maximum. So you use so equal to now 0.75. Our D is 500. So what is our S maximum? Anybody have the answer?
375.
375.
Okay, good. Okay, thank you. 375. So, S is equal to 75, lesser than S max. So, okay. So, we use H6 75 millimeter center to center. C stroke C means center to center. Okay, this one is near support. Near support because near the support the spacing is closer. Okay, this one 75 because our bending the value of the shear force. Okay, let's say this is the be careful. Okay, this is our shear force diagram. It's like this one. Okay, the maximum is occurred near the support. Let's say this is support and this is also support. The maximum occurred near the maximum shear. Okay, maximum shear occurred near the support. So we have to provide closer link here and here near the support. But at the midspan, the shear forces decreases. So we can reduce the space for economical design. Okay, we can use very close for the whole beam, but this is uneconomic. Okay, for the sake of economy, to save the budget, to save the resources of steel, so we can reduce the link at the middle span. Okay, and then so we design step number 4 is we design the minimum link. Okay, this is for midspan, near the midspan. So the ASW, we use the equation. Okay, I provide here. This is the equation. This is the equation for minimum link, equal to 0.08 times BW times the FCK, okay, square root of FCK, and then divide by FYK. Okay, the answer is 0.08 times BW is 225 times 30. Okay, square root of 30 divide by 500. Okay, what is the value of ASW now? Sorry, this is ASW over S. Okay, any value? Any answer, class?
0.197.
Okay,
0.197.
197. Okay, we can assume as 0.2. Okay, thank you. Okay, so just use like this one. Okay, just repeat this step. Spacing is equal to, okay, we just first we use the similar size. Okay, to ease the construction. If you use H6 at the support, okay, near the support you use a diameter of 6. So at the middle also you use the same diameter. Okay, same diameters. This is to ease the process of constructions. Okay, so use H6. So ASW is equal to 56.5 mm square. So spacing S is equal to ASW over 0.2. This is the 0.2 we get. Okay, we just this equation actually. Okay, ASW over S is equal to 0.2. So S is equal to, okay, we just change the position of S, okay, to the 0.2. Now equal to 56.5 divided by 0.2. What is our new S? Any answer?
282.5.
Okay, thank you. 282.5 mm. So, what is the practical value to use? Okay, what is the value, practical value of S to use instead of 282.5?
275.
Okay, thank you. Good. Use 275 mm. Okay, this is practical. Okay, to install. Okay, so use H6 275 mm, center to center. This is okay near the midspan. Okay, now we have to check the shear resistance of minimum link. Okay, we can use this equation. V minimum is equal to ASW over S times 0.78 D times FYK times cotangent theta, where theta is still equal to 22 degree, so equal to 56.5 divide by, okay, use this S 275 and then 0.78 times 500 times 500 times 2.5. Okay, what is the value of V minimum? Okay, any answer? Any answer for V minimum? Hello class, any answer for this one? Are you still with me?
I got 159.09.
Okay, 100.2 lah. Thank you. Okay, kilonewton.
I got. Oh yeah.
Okay, 100.2. Okay, so now we have to find the distance. Okay, find the distance. Find distance X. Okay, for shear reinforcement. Okay, because we want to know what is the distance, we can use H675 and H6 275. Okay, so this is okay. Back to our basic. This is our okay. Our shear force diagram. Okay. Okay, so the basic is very simple. So here we have 360, and then here let's say we have 100.2 kilonewton. So here to here we assume as okay from here. Okay, so here to here is our value of X. So here is okay to the middle. To the middle is L over 2. Okay, and then we assume here is Y. Okay, so to find the value of X, because later as I mentioned before, from here to here we can use H675, and from here to here the X is equal because the beam is similar. Okay, I mean okay, so here also H675, but at the midspan we can use H6275. Okay, we can save the cost there. So the calculation is very easy. So y over x here, y over x is equal to, okay, the tangent, let's say here, okay, is equal to 360 360 over here to here is equal to L over 2, right? L over 2. So x is equal to okay, x is equal to, sorry, what was the answer? Wait, y. Okay, sorry, y is equal to this one. Okay, sorry. just do it slowly. Okay. Y is equal to 360 minus 100.2. Okay, this is our Y, and divide by X. Okay, and then it's equal to 360. So 6 is our L. Okay. So can you find the value of X for me? Very simple.
$120.
What?
Wait.
Divide by 360. Any answer for the X? Tak apalah ya, kita lama. Sorry.
2.165.
2.165 2.165, so we just close it to 2.2 meter. Okay, so the S is 2.2 meter, means 2.2 meter from support we can use H675. Okay, sorry, I have to I just use this page. Okay, and then step number 5 is we check for the additional longitudinal reinforcement. Okay, this is due to the shear stress. So additional tensile force. Okay, F TD is equal to 0.5 VED times cotangent theta. So it's equal to 0.5 times 360 our VED times 2.5. Okay, what is the value of FTD now? Any answer?
450.
Okay, thank you. 450 kilonewton. Okay, next we have to check for additional tension reinforcement. AS is equal to FTD divided by 0.87 FYK equal to 450 times 10 to the power of 3 divided by 0.87 times 500. What is the value of AS now? Additional tension reinforcement. Any answer?
$1034.
Okay, thank you. 1034 mm square. So we use, okay, for additional tensile reinforcement is at the bottom here. Can you see here our cross sectional here is we have 2 plus 4. Okay, 2 plus 4 of steel reinforcement at the bottom here. So we may use the same size of of the bottom reinforcement. So the size is 20. So we use H20. Use how many H20 to cater for 1034. Okay, we check the table of reinforcement. Which one? Okay, H20, which is greater than 1034. How many
4.
H20? Okay, 4. Thank you. So this one, okay, 1260, the total AS. So use 4 H20. So the AS is equal to 1260 mm square greater than 1034. Okay, so this is the final. Okay, to be added. Okay, to be added to AS for flexure support after curtailment. Okay, the curtailment will be teach by Ir Salimi this coming Sunday. Okay, make sure you attend the class. Okay, so you can do the final detailing. The detailing is like this one. The cross section detailing. Okay, the detailing. Okay, let's say we have our beam here. Okay, let's say this is our beam. This is the column, the support. Okay, this is the beam, support to support, because our beam is simply supported. Okay, here. And also here. Okay, so this is our beam. So we just refer back to our the situation given for the main reinforcement. So is at the top we have 2H20, 2H16. So this is our main reinforcement. At the top we place. Okay, and then we may label it. Okay, here is 2H16, and at the bottom we have here from support. We drag over here. Okay, 1, 2. Okay, we have 1, 2, 3, 4. Okay, 4 at the bottom. So, okay, here is 4H20, and then 2 at the support maybe here. This is curtailment. Okay, lesser. Okay, okay, here. Okay, 2H20. Okay, because our bending moment, we refer back to our, recall back our knowledge. Okay, this is our shear force diagram for simply supported beam. The shear is maximum occurred at near the support, but for the bending moment, okay, that's why, okay, the shear is maximum occurred to the support. So that's why at the support we have our reinforcement. So like this one. Okay, this is our shear reinforcement near the support, maybe here to here. This is how to detail our beam. Okay, you can do the calculation, but the workers did not understand the calculation. They only consider the drawing. Okay, so this is H675. Okay, and then also at the another support here to here. Okay, H675, and then okay, the length of this is the length of X we calculate before. X is equal to 2.2 meters. Okay, here also X is equal to 2.2 meters. Okay, and then the rest at the mid span we can use. Okay, what is our reinforcement? Can somebody tell me? Okay, this is how to do the detailing. Okay, H6. What? Check back at the mid span.
275.
Okay, good. 275. Okay. So, okay, reflect back our knowledge on the structural analysis. This is, okay, since at the near the support, the shear is very maximum. Okay, it's very high here. So that's why we use closer link. And then near the midspan, okay, the value of shear force is decreases. So we may reduce the spacing. However, for the bending moment of the simply supported beam, this is the bending moment. The bending moment is maximum at the top, at the midspan. Okay, at the midspan. So that's why at the midspan we provide here 6. Okay, the total of 6H20 here. Okay, 6H20. Okay, this is the cross section. Okay, you can create your own cross section, and then here to the support, we provide this one, okay, to be added, this one to be added to as for flexure support. So this one we use 4H20. So we just use this one, okay. We just take advantage of our previous main reinforcement for bending at the bottom. Okay, any questions up to now? Yeah, I have exercise to you later, 8A to 8D, 4 questions. Okay, this is the step. Okay, you have to submit to me later as a proof of attendance and proof of participations, whatever notes you write down in our sessions today. Okay. Any question, class? Okay, so if you don't have questions, so we will stop our exercise 8 here and see you in next video. Thank you very much.